All right, welcome to Math Stat 341, Lecture 26. This is the technical lecture. So we're going to prove the central limit theorem modulo a couple of results. The biggest ones are things coming from complex analysis about convergence. So the idea is we're going to be looking at moment-generating functions. Moment-generating functions do not always exist. When they exist in a neighborhood about the origin, you can often deduce a lot of nice things. So for us, a moment-generating function is the expected value of e to the tx. And I'm going to just write a couple of results. So z is always going to be a standard normal. Its moment-generating function is e to the t squared over 2. The moment-generating function of ax plus b of t, well, when you just put in t times ax plus b and just use properties of expectation, this is in the lecture you're supposed to watch at home. It's in the book. You should do these calculations. You should prove these results carefully. This is a good way to make sure you are comfortable with the integration. This is going to just be e to the bt, and then the moment-generating function of x evaluated at a times t. The moment-generating function of x1 plus xn of t, if they're independent, is going to be the product k equals 1 to n, the moment-generating function of xk to the t. I don't want to use I because really what should be looking in the background is the characteristic function, which is the expected value of e to the I tx, where I is the square root of -1. If you look at the characteristic function is always defined. And the reason is the absolute value of e to the I theta is always 1 if theta is real. So it's going to be integrable. Unfortunately here, if t and x have the same sign, this is going to be growing exponentially fast. And thus it's not always going to converge. So the characteristic function has the advantage of always existing. The next one is the moment-generating function of x, where this is Poisson with parameter lambda, is going to be e to the lambda e to the t minus 1. So we've done that calculation before. It has a very nice explicit form. So the main result, if xn are independent and nice, and if we let zn equal x1 plus xn minus n mu over sigma square roots of n, then we have the following. Anybody want to guess what the expected value of zn is? Yes?
0?
0. So the expected value of a sum is the sum of the expected values. So let's forget about the denominator for a second. Each one of these, I should probably say independent nice, mean mu, variance sigma squared. So we'll even say identically distributed. And then it becomes a game how much you can weaken these conditions. And so right now in a first course on probability, I don't want to worry about what's the most general case we can study. I'm going to study sufficiently nice cases, because even in these cases, we have to appeal to results from complex analysis. We should hopefully have the classes for next year finalized soon, and then I can tell you hopefully that complex analysis will be offered. Given that it was not offered this year, it's quite likely it will be offered next year. And that's what you need to prove a lot of these things rigorously. The other thing, of course, is, I'm adding my x1 through xn, and then I'm subtracting off n times the mu, and I'm dividing by sigma squared of n. This process is called standardization, or standardizing the sum. And the idea is to convert to something that's nice. This is why we only have tables of logarithms either base 2, base 10, or base e. Because if you know logarithms in one base, you can convert to another. This is why a lot of textbooks only have probabilities of the standard normal, because if you know that, you can convert to any normal by doing a change of variables. It's all about a change of variables, so we're going to show that things converge to the standard normal rather than showing that things converge to a normal. What do you think the variance of Zn is? What do you think I've chosen my variance to be? What nice number? 1. I can't choose it to be 0. If the variance is 0, then all the values are the same. So I can adjust any non-zero positive number. I can rescale it to be 1. And we use the fact that the variance of a sum is the sum of the variances if independent. It doesn't matter that I've subtracted off n times the mean. That doesn't change the fluctuations. Each one of these has variance sigma squared. And then you square the coefficient down below. If you have alpha x, its variance is alpha squared times the variance of x. Otherwise, if you had a negative number like alpha, if you had negative 3x, you wouldn't say the variance of that is negative 3 times the variance of x. You can't have a negative variance. So the only things that would make sense is the absolute value of negative 3 or the square of 3. And it makes sense that it's the square because when you measure fluctuations, it's the standard deviation or the square root. So if I multiply all my values by 3, I should increase my standard deviation by 3. And thus the variance should increase by 9. So when you go through and do the algebra, I strongly encourage you to make sure you can do this. You get the variance of Zn equals 1. So then, if the moment generating function of Zn converges to the moment generating function of Z, which is the standard normal, then the density of Zn, or the cumulative distribution function, converges to the cumulative distribution function of Z. And in many situations, you'll have the densities converging as well. I am being very vague in terms of what I mean by convergence. In all the situations we'll be looking at, we can actually be a little bit more explicit. The idea is we're going to show the moment generating function converges to the moment generating function of the standard normal, and then use that to say, well, if the moment generating functions converge, the reason they converge is because they have the same densities. What is the moment generating function? The moment generating function is a power series whose coefficients are the moments. So this is basically saying we know the moments are converging to the moments of the standard normal. The only thing that can have the moments of the standard normal is the standard normal. And of course we know that this is bullshit, right? Real analysis is hard. We have this nasty function where all of its Taylor coefficients are 0. And so this function, and e to the negative 1 over x squared multiplied by 1701 plus sine of x and sine of x. These two functions have the same Taylor series at 0. We can't distinguish them from the Taylor series. It's the same issue with knowing the moments. Knowing the moments is not enough to uniquely determine the probability distribution. In an advanced class, you would have a lot of fun delving into, well, when do the moments uniquely determine? What must be true about the moments so that I can say, aha, I now know what the distribution is. This is the result we will be using the black box result from complex analysis. That if the moment generating functions converge, the only way that can really happen is if the densities converge. And that's where we get our central limit theorem from. Right? Everybody clear on the rules of the game? I'm not going to prove this. I may give you a link to some lectures on complex analysis where we go into some of the details behind this in terms of what's going on, and then just free up some class time to do more coding or more just other types of problems. All right. So in terms of doing the proof, I could just do the proof in general and start off doing the proof in general. It's a mostly straightforward but a little bit painful algebra excursion. So what I thought I would do is I would first do the proof in a special case, and on the final, you will do the proof in a different special case. I have chosen to look at the Poisson random variable. There's a lot of wonderful things about the Poisson random variable. And you will see as we do the algebra why the Poisson random variable is so nice.
One of the reasons that makes it so nice is we have a beautiful expression for its moment-generating function. We have a closed-form expression. I can't emphasize enough how valuable it is to have a closed-form expression. Most of the time, we won't. If I give you a general probability distribution, it's going to have a hellish moment-generating function. But that's okay. There'll be ways around it. You should always look at theorems and focus on the conditions. What's being assumed? And either I'm assuming things to make my life easy, or if I drop these assumptions, things are wrong. I'm not saying what it means to be nice. At a bare minimum, I want the moment-generating function to exist, so that means all the moments have to be finite, because if any moments were infinite, the moment-generating function wouldn't exist. So I will want the moment-generating functions to exist in some neighborhood about the origin. I am assuming something about the means and the variances, that they exist. I'm assuming identically distributed. I am not assuming anything about the higher moments other than they exist. Notice that when I standardize, the higher moments do not come into play. So whenever you get a theorem, you want to know not only why is it true, but how good is it? Chebyshev's theorem, good or bad? What do you think? That's the right answer. Good if. That's the answer. It depends. Chebyshev works for everything. So if I don't have anything else, it's good. If I have other things, I don't want to use Chebyshev. There are things that are better. This does not depend on the higher moments. That's where the universality is coming from. That's why it doesn't matter what the x's are. It doesn't matter what their shape is. That's the amazing part. That's the miracle. The shape should matter. How does the shape matter? It matters in lower order terms. It matters in the rate of convergence. I'm not talking about how quickly this happens, just that it happens. Okay? You want to know how long do I need to wait? If you're taking stats, what do they normally tell you for n? 30. Sounds good. Nice number. Typically, if n is 30, you should have decent convergence. But I can cook up some distributions where 30 will not be enough to have good convergence. And you would have to go significantly further. But for most of the things you'll encounter, n equals 30 is already enough to start to see the limiting behavior. Notice that when we're standardizing, if I give you any probability distribution, adjusting the mean is just sliding everything down. We talked about this when we did the baseball problem. It's not a big deal to adjust the mean. Right? So that's one parameter that comes in. The next thing is adjusting the variance. Well, that's just rescaling things, measuring things in meters rather than feet. I can rescale my x-axis. Once I've slid things down and rescaled the x-axis, I no longer have any freedom. That's why I have to stop here. I can only use the first two moments. So it's really the third moment that's the first moment that starts to show the shape of a distribution. Any distribution that's nice, I can always adjust to have essentially mean zero. And in fact, I have a paper with 2 undergraduates from a couple of years ago where there were 4 candidates for what the limiting behavior should be. And we showed, well, if you adjust so that they all have mean 0 and they all have variance 1, the 4 candidates are almost impossible to distinguish. They look almost the same. There is a way to distinguish them, and that's one of the things that made the paper. And I'll send you a link to that paper later today. So once we subtract off the mean, once we renormalize by dividing by the standard deviation of the top, we have no more degrees of freedom. The higher moments affect the rate of convergence. If your distribution is symmetric about the mean, then the third centered moment will vanish, and it will be the fourth moment that will be the first moment that emerges. So what I want to do now is I want to prove essentially that the moment generating function of the Poisson, if I take n independent copies, converges to that of the moment generating function of the standard normal. I will do the calculation as general as possible for as long as possible, and then just record, okay, and at this point, I'm going to finally break down and use the fact that I know what the moment generating function is. And then that will allow us to do the proof in general. So I will record that for the Poisson, it has a mean of lambda and a variance of lambda squared. we have a lot of different ways we could calculate the mean and the variance. One way we can do it is we can use the method of differentiating identities. Another is we could take derivatives of the moment generating function. Another is we could expand the moment generating function. And if you look at what's going on here, what is the most natural place to evaluate the moment generating function? What value of t? If you had to choose a value of t, what value would you choose? 0. Why would you choose t equals 0? You're taking the expected value of 1. So I tell you, no matter what x is, I'm always going to give you 1. All right? I'm pretty sure I can calculate that integral. It's always going to be 1. So when t equals 0, all moment generating functions are 1. If I put in t equals 0 here, e to the 0 is 1. Oh, that perfectly cancels with the negative 1 over here. And I get e to the 0, which is just 1. So this expression over here is actually going to just be t plus crap. Okay. So I'll go through the algebra and show just how you can expand this out, because it's worth playing a little bit with Taylor series. So we have e to the lambda, e to the t minus 1. This is 1 plus lambda e to the t minus 1 plus lambda e to the t minus 1 squared over 2 factorial plus dot, 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 dot. The reason I can do it like this is I know this term has to be at least everything is a multiple of t, everything is a multiple of t squared, everything here is going to be multiple of t cubed or higher. If I want to just find the mean and the variance, none of these terms are going to matter. So I'm going to get, it's 1 plus lambda, and then e to the t is going to be t plus t squared over 2 factorial. Do I need to worry about anything else? Not if I just want to find the first two moments. Now for the next one, do I need to worry about the t squared term here? No. Because that, when I square it, will give me a t to the 4th, or if it hits the t, it'll give me a t cubed. The only thing that's going to matter here is when I square this out, it's just going to be the t part. So I would get lambda squared t squared over 2 factorial. All right, so now, if I just combine, I get 1 plus lambda t. I have lambda over 2 factorial plus lambda squared over 2 factorial. I'm wondering if I actually have a typo now. Lambda plus lambda squared over 2 factorial t squared. So now, what's the expected value of x? That's just going to be the first derivative. That will just be lambda. What's the expected value of x squared? Yes?
It's the coefficient of t squared.
So I get lambda plus lambda squared over 2 factorial. Do I have to do anything else? I have to multiply by 2 factorial. Because remember, the way we define the moment generating function, it's going to be the sum of mu n t to the n over n factorial. So I actually have to remember to multiply by the 2 factorial. So then the variance would be the expected value of x squared minus the expected value of x squared. So I'd get lambda squared plus lambda minus lambda squared. So actually I think I had the wrong answer over here. So I think that for the Poisson, the variance is not lambda squared, but the variance is actually lambda. So that was a mistake. A somewhat deliberate mistake. Why couldn't I notice that? Because lambda doesn't have units here. That's the problem. In a lot of other things, when we have the exponential random variable, lambda has the same units as x. X could be in meters. Over here, in a Poisson process, lambda is a count. Think of it as how many accidents in an intersection. Or if you've taken statistics, I think it's just German horse injuries, right? How many German officers have been injured on horses? It's a count. Because it's a count, I don't have units, and I can't say, well, it should be the square. So this is an extremely common mistake to make. So sigma should be the square root of lambda for the Poisson process. Okay? Lots of ways you can do the calculation. If you don't like doing the algebra like this, you can just take the derivatives. And if I take the derivative twice, the 2 factorial is now going to cancel with the 2 factorial down there. And if I take the second derivative at 0, that will just give me the second centered moment. And from that, I can then calculate the variance. Okay. Any questions on the calculation we've done up till now? So this is just to make sure we have the correct answer for the mean of the Poisson, and we have the correct answer for the variance. So we've got the variance of the Poisson is lambda, standard deviation, square root of lambda. Now we're going to calculate how sums of Poisson. Okay. Now, we actually know something about sums of Poisson random variables. What do we know about sums of Poisson random variables? They're Poisson with the parameters just shifting. So I'm not going to use that information because I want to try to mimic the proof as much as possible. But if you want, as a nice exercise, try to prove directly by looking at sums of Poisson. It's going to be a very similar argument. So I will do proof for Poisson. So we want the moment generating function of z n of t. And this is going to be the moment generating function of x1 plus xn minus n mu over sigma square root of n of t. And again, I'm not going to plug in what is mu and what is sigma for the Poisson because I want to keep this as general as long as possible. This is all in the book going through the algebra like this. So if you don't want to write down the algebra and just follow it, absolutely fine. All right, so the first thing is let's look at all the different wonderful properties we have. So what wonderful properties do we have? We have the moment generating function of ax plus b is e to the bt, the moment generating function of x at at. So we can use that to slowly expand things out. So let's just, first of all, I'll write this really slowly as the moment generating function of x1 over sigma square root of n plus xn over sigma square root of n minus square root of n mu over sigma times t. So the first thing is I'm going to keep all of this together and just use b equals negative square root of n mu over sigma. And I will get that this is going to be e to the negative square root of n mu over sigma t. And now I'll have the moment generating function of x1 over sigma root n plus xn over sigma root n of t. The next thing I'll do is I'll use the moment generating function of a sum of independent random variables is the product of the moment generating functions. So this will be e to the negative square root of n mu over sigma t. The nice thing is this is really a follow your nose proof. This is why the only notes I have for me is what I wanted to write on the board today. Any Isaac Asimov fans here? Anybody ever read the Foundation series? So very similar to the first Foundation, my path is predetermined. I have no choice in the algebra I am about to do. It is literally just keep applying stuff. So now it's the same as the product k goes from 1 to n of the moment generating function of xk over sigma square root of n of t. And now for each one of these, I now use a is 1 over sigma square root of n. And now I get, this is e to the negative square root of n mu over sigma t, product k goes from 1 to n, the moment generating function of xk at t over sigma square root of n. So this is the moment generating function of Zn of t. And I will box this off as this is going to be quite important. So I've now got the moment generating function of Zn in terms of a product of the moment generating functions. I'm raising it, if they're all equal, then I can replace all of these with just the moment generating function of x1. So can I erase the algebra up here and just write the answer right here? Is everybody okay with that? We need to conserve board space. So we'll get e to the negative square root of n mu over sigma t, and then we'll get the moment generating function of x1 at t over sigma square root of n raised to the nth power. All right. And that's going to be the expression we're going to want to look at.
Is that the whole thing raised to the nth
No,
power?
just this part over here. Because we had a product from 1 to n of this. And so because they're all identically distributed, it's just that to the nth power. Okay? So after doing some algebra, we just have this expression for the moment generating function of the standardization of x1 plus xn minus n mu over sigma square root of n. We have this. And we want to show that this converges to e to the t squared over 2. Now, if you could choose to evaluate the moment generating function at any point, what would be your point? What would you choose? 0. What happens as n gets very, very large for fixed t? Where are we evaluating this? In the limit, we're evaluating this at 0. So we're evaluating this at the best place to evaluate a moment generating function, at 0. Now, unfortunately, we're not exactly evaluating it at 0. We're moving it off by just a little bit. Well, it should still be very close to 1. But then we're raising it to a large power. So if I give you 1 plus, x over n, that's very close to 1. But now if I raise that to the nth power, that's e to the x. And so we have to be careful. We have to take into account the fact that we're evaluating it at the end. All right. You should have a Pavlovian response now. What is your Pavlovian response? Take logs, right? There's a product. Whenever you have a product, take logs. And we've seen before when we did the central limit theorem for the coin toss, how easy it was to mix up limits. So if we take logs, we get the log of the moment generating function of Zn of t. Well, this becomes nice. Now it's going to just be negative square root of n mu over sigma t plus n times the log of the moment generating function of x1 at t over sigma square root of n. And if this is really close to 1, then the log is really close to 0. Okay, so this ends the general nonsense. If you could choose a moment generating function to take a log of, okay, you get your choice. It should be clear why I love the Poisson moment generating function. Ask me which kid I love the most. Yeah, I can't answer that. When they were young, it's whoever's sleeping better. Now I can't say. Over here, why does this moment generating function beat the crap out of most generating functions? What's so nice about this for what we need to do?
Closed form.
Well, it's more than just a closed form. What's nice about this closed form? What do I need to take to this? What do I need to apply to this?
Log just gives you the exponent.
Yeah, if I take the log of this, I just get lambda e to the t minus 1. So this is screaming at you, please take my logarithm. I will oblige. happily, right? And so now we get that this is just negative square root of n. Now let's plug in what things are. Mu is equal to lambda, right? Sigma is square root of lambda. And then we have plus n. And now the log of the moment generating function, so it's just going to be lambda. And then we have e at the input. And the input is going to be t over sigma, which is square root of lambda, square root of n, minus 1.
Were you supposed to have a t in the first term?
Yes, there's supposed to be a t in the first term. I was about to say that's wrong here. Okay, that looks good now. Now, t is fixed. So as I start to expand this, the fact that I have a square root of n means I probably don't need that many terms. But I multiply by an n. So because I'm multiplying by an n, a couple of terms could survive for a while, but eventually they're not going to matter. So let's continue to do the algebra. I've got a negative square root of n. Lambda divided by square root of lambda is square root of lambda, t, plus n lambda. And now the first term, when I expand this, I get 1 minus 1, that cancels. So then I'll get a t over square root of lambda, square root of n. The next term is I square this, so I'll get a t squared over lambda n, and then I have a 1 over 2 factorial. The next piece is I cube it, so I'll have a t cubed over, there'll be a 3 factorial, which is 6. I'll have a lambda to the 3 halves and n to the 3 halves plus more crap. We multiply by n. This piece is of size 1 over square root of n, so when you multiply by n, that's quite large. All right, so I have negative square root of n, square root of lambda t. Now when n hits this, the square root of n makes the square root of lambda up top, square root of n makes the square root of n, so this is going to be square root of n, square root of lambda t. Oh, beautiful, perfectly canceling. The next term, the n cancels down here, the lambda cancels, we get a t squared over 2, and then the next piece is going to look like a t cubed over 6 square roots of lambda, and then it's going to be a square root of n down below. Because we have an n to the 3 halves, we multiply by an n, we're still left with a square root of n down below. And all the other stuff from here onward is going to have even higher powers of n down below. So in the limit, does not matter. And so what we'll get is we'll get t squared over 2 plus small. Okay? And now you can begin to see where the higher moments matter. Where are the higher moments? Well, they're coming in over here. This is where your third moment would be. Your third moment would be controlling that first error term. And that would be controlling the rate of convergence. So there's a beautiful theorem. It's the Berry-Essen theorem that quantifies rates of convergence. For a first course, we don't want to go into that, but it's nice to know what's out there. And it's nice to know what would you need to do a better job. Don't be careless. Just keep track of this term. Don't throw it away. And that will be your main error term. And then your next term, you would have a 1 over n. That would be significantly smaller. So we know the log goes to t squared over 2 plus something tending to 0. Well, if the log goes to e to the t squared over 2, then you get the moment generating function of Zn is e to the t squared over 2 plus small. And it's converging to the moment generating function of the standard normal. And that's the proof. So this is the proof in the case of the Poisson random variable. Up to here, it was perfectly general. Only from this point onward did we then start to use the fact that we have a Poisson random variable, we know its moment generating function. And we got that the moment generating function had a beautiful expansion and everything canceled perfectly. So all we have to do now is just go back here and use the fact that we have a general moment generating function and not the specific one. All right? I think it's nice to see a special case first, get a sense of big picture what's going on, and now let's just do the calculation in full generality. If there's time, at the end of today I will use this to prove, or at least make very plausible Stirling's formula. Is everybody happy with here? On the exam, this is the level of problem I will give you. I will give you something which has a nice moment generating function and ask you to basically do this. If you just reproduce from the book the general proof and then at the very end substitute, that will be worth nothing. Right? I want you to bypass the general proof and use specific properties of a nice moment generating function. Not surprisingly, I saved the nicest for myself. Right? It's good to be the king. Anybody know that reference? So you do have extra credit for Isaac Asimov. Make sure you email me. All right. We ready? So let's recall the moment generating function of x of t is 1 plus mu of t plus mu 2 prime t squared over 2 factorial plus higher. I'm not going to bother working with the higher. They will always have an extra square root of n in the denominator, and they won't matter in the limit. Okay? So I'm not going to bother putting in these pieces here. Whenever you have long, complicated algebra, it's best to do it in stages and steps. Here's my moment generating function. Now, let's evaluate it at t over sigma squared of n before we jump to the logarithm. So now we get the moment generating function of x1 at t over sigma squared of n is going to be 1 plus mu t over sigma root n plus mu 2 prime, and I have to take the square of this, so I'll get t squared over 2 sigma squared n plus higher. And the higher term, the higher order term, is going to have at least a 1 over n to the 3 halves. At least 1 over n to the 3 halves. So we really won't have to worry about that. So when n is very, very large, this is essentially 1. It's 1 plus a little bit. So if I take the log of 1 plus u, this is equal to u minus u squared over 2 plus u cubed over 3, and so on and so on and so on. This is the Taylor series expansion of the log of 1 plus u. So my u is going to be all this crap. So if this is u, everything here has at least a t. So when I look at u squared, everything is going to have at least a t squared. When I look at u cubed, everything is going to have at least a t cubed. But I don't care about dependence on t. What do I care about? Dependence on... It's not t that I care about. What do I care about? What's the key parameter here that's going to infinity? N. So if I look over here, the best is over here. This is the largest one. It's 1 over square root of n. This is much larger than this term. It's larger by a factor of square root of n. So this term over here, its main term is going to be like a 1 over square root of n. Its secondary term is going to be like a 1 over n. Its tertiary term is going to be like a 1 over n to the 3 halves. When I multiply by n, only the first two terms can survive. The last term, the 1 over n to the 3 halves, won't matter. When I look at the squared term, I have to square this thing. Well, this times itself will give me a 1 over n. That will survive when I hit it with an n. When the t hits the t squared, I have an n to the 3 halves. That won't survive when I hit it with an n. When the t squared hits the t squared, I have a 1 over n squared. That won't survive. I'm only going to keep terms that survive when I multiply by n. Okay? So this is where it's nice to have even more blackboard space than we do. All right. So now, if we look at what's going on, the log of the moment generating function of Zn at t is equal to the following. So the first is this piece over here, minus square root of n mu over sigma t. That's coming from this part over here. Now we have plus n times now we have this crap over here. All right? So this is my u. I get that in. So I get a mu t over sigma square root of n plus mu 2 prime t squared over 2 sigma squared n plus other stuff. Then I have a minus n, and now I have to square this whole thing. Oh, it didn't break. I have to square this whole thing and divide by 2. So I'll have a minus n over 2, and then the only thing that matters is the mu t sigma root n times itself. So I'll have a sigma squared t, a mu squared t squared sigma squared n plus stuff that doesn't matter plus n times stuff that doesn't matter. Okay? Any questions? Now it is time for the algebra miracle. Right? This term is going off to infinity with n, but let's see. N divided by square root of n is square root of n, mu, sigma, t, they perfectly cancel. So this cancels with that. Great. I'm left with two terms now. They both have a t squared. The n cancels down there, the n cancels down there, so the n's cancel. Good. So I get a mu 2 prime minus mu squared over 2 t squared. What's mu 2 prime? Oh, and then plus lower. What's mu 2 prime minus mu squared? I'm sorry?
The variance.
It's the variance. And if you notice right over here, I forgot that there's a sigma squared that I should have been copying down. And so when I remember to put down the sigma squared, that now cancels with that because it's the variance, and you get, miracle, t squared over 2 plus lower. And that's the proof. So that means the moment generating function of Zn of t is e to the t squared over 2 plus lower. And 5 minutes to spare. This is not a lecture you want to split into two classes. The proof is extremely similar to the special case of the Poisson. The difference is, for the Poisson, it was screaming, take my logarithm. I will be really nice. I promise I'll be really nice if you take my logarithm. And it was. For this one, you have to do a little bit more work. No one wants to see the algebra going into excruciating detail. I hope that this was enough so that you could say, well, yeah, if we did a little bit better job, if we were a little bit more careful, all the terms that survived would have at least an extra 1 over root n in the denominator. And then we need some results from analysis, some kind of, well, we'll have these infinite series. Maybe each one is small, but maybe when we add them up, things are exploding. That's where you need the moment generating functions to converge. That just will guarantee that all this lower order stuff can't catastrophically reinforce. Okay? It's not the best use of time to go through that. All right. Any questions about the proof? All right, we've got 5 minutes left, and we have the beautiful Poisson random variable on the board. So let's look at a bunch of Poissons. So let's say each xk is Poisson with parameter 1. Let's let Zn be x1 plus xn. So if I do it this way, what should this converge to? Yes?
Shouldn't it be normal, but your mean is, you have to add the n mu?
Yes. So my mean should be n times mu. And since mu is 1, my mean should be n. So this should converge to a normal with mean n and variance 1. I'm just not sure right now if I want to do with the sigma over root n over here, or if I want to even avoid that. And maybe just even look at, yn is x1 plus xn, which should converge to normal n, and then what should the variance be? Well, what's nice is when lambda equals 1, the variance and the standard deviation doesn't matter if it's square root of lambda or lambda, lambda's 1. So this should just be a variance of n. So that might be a good one to look at the y's. We know what the density is for the Poisson. So the density function of one Poisson, let's use m, is equal to lambda, which is 1 to the m, e to the minus m over m factorial. Now if I do yn, this is the sum of the x1, so I think this is the one I want. This is a Poisson with parameter n. So this should be n to the m, e to the minus m over m factorial. And this should be converging to a normal with mean n and variance n. Okay. What's the best place? So the density function for the normal, so let's say w is normal with mean n and variance n. So the density is 1 over square root of 2 pi e to the negative x minus n squared over 2n. What value do you want to evaluate this density at? When you look at this, it should be screaming at you what choice of x to take. N. So at x equals n, density is 1 over square root of 2 pi. But we know yn, which is Poisson with parameter n, is converging to a normal with mean n and variance n. When you look at the Poisson density, what value should I take for m? What's a really good choice for m? What did we take here for the density? N. What would be a really good choice to take down here? N. So if we take n,
Is it supposed to be n in the density? Like 1 over 2 pi n?
oh yes, thank you. 1 over 2 pi n. Yes, thank you. And that would be very important to have there, so thank you. So if I take m equals n, I get n to the n, e to the minus n, over n factorial, should be approximately the density here, which is 1 over square root of 2 pi n. So if I cross multiply, I get n factorial should be about n to the n, e to the minus n, square root of 2 pi n. There's Stirling's formula. So this gives you another reason why I wanted to do the central limit theorem in the case of Stirling, in the case of a Poisson random variable. Not only are we getting the central limit theorem, we actually get Stirling's formula. Now you need to make this a little bit more rigorous. This is not quite a fully rigorous proof, but it's close. It seems like something is going on here. We're even getting the square root of 2 pi n. All right, so this is a very good place to stop.